Let's go.
Great.
Let's go with 5.4. So we have here is probably, I would say, the most interesting section in the textbook. Interesting in the fact that we're going to try to make everything into a normal curve. So like, how does that happen, right? Because like test scores, on a test score, the average could be like 70%, right? How do you make that so that it just comes down into a normal curve again? Like, I don't know. Let's see what happens here. So sampling distributions, how we handle those, and then eventually the central limit theorem. Oh, honesty question. Raise your hand if you took a look at 5.4 and 5.5 prior to coming to class, sitting down today. I got two today. This is cool. The highest. This is the max. We got a max today of 2. All right, so sampling distributions, let's go. Let's talk about that first here. So I didn't highlight this here, but these guys should be highlighted. So a sampling distribution of a sample statistic that is formed when random samples of size n are repeatedly taken from a distribution. Okay, what in the world? We'll talk about in just a second here. In fact, let me actually get it out to here. I will be highlighting so I can have it for the next group. You guys talk to me. Did highlighting help in the notes or no?
Yeah.
Good, okay.
I feel like the last 2 chapters you didn't highlight it.
All right, okay.
5.2 and 5.2.
Then I gotta highlight more. Okay, I'll do that then. So just have to write as a definition. Here's our definition: the probability distribution of a sample statistic, right? Because it's a sample set that is formed when random samples of size n are repeatedly taken from a population. So somewhat funny at first. So what we do is we take from a population and we just take sample statistic of sizes n. So let's say we had a population of 100 data points. And so we said, you know what, we're just going to take 20 of those samples. We take 20 and then we do something with it, right? And then we put the 20 back. Then we take another 20, we do something with it, put them back. And so we keep on repeating that process. And lo and behold, it gives us something very interesting. But we'll see what that is in just a bit. Okay, and then this one right here, what we want to do with it is do this right here. I could just go like this here. I could make this bigger. There you go. That would make it. And then I know how many slides I have. Okay. More 33. We're going to cover 33 before break. If the sample statistic is a sample mean, the distribution, again, another thing is the sampling distribution of a sample means. Too many words here. What are we saying? This is what we're going to do. We have 100 data points. We're going to take 20 of them at a time. We're going to take 20 of them at a time, and we're going to take the average of those 20s. Put them back. Take another sample of 20. Figure out the average or the mean. Put it back. Then we do it again and again and again and again and again and again. And 2 things come out of it, which are super interesting. Sorry, making you write a lot here. Got 1, 2 of those. Let's see if we have any more of writing down a lot. Okay, good, good. I think everybody's got it. So picture-wise, what does this look like? Let's go for it here. So here it is. This right here, the rectangle around, that is our population. That's all the data points we have. We're good? So then we do random sample one. And let's just say we pick these people here. And what we do is we figure out if we want to, we can just do the mean. Remember that little bar line on top means the average for samples. Is that right? So do sample one. And then we do is we put them all back. Then we just randomly select another group of data points right here. And we do the average on that yellow group there. And then we do it again on a third group and a fourth group and a fifth group. And we can keep on going. 6, 7, 8, 9. We could do this 100 times. We could do this 1,000,000 times. We good? But what's happening here? So 2 things happen. 3 things happen. Well, let's take out the 2. 2 things happen. First is this little part happens. So if you take all the averages and then you actually take the averages of the averages, it's kind of crazy, right? You take the mean of all the sample means you've got. It's going to happen. What's going to happen is it's actually going to give you the mean of the population itself. And we're going to do the exact same thing for the standard deviation. And then we're going to do something extra. We're going to take the standard deviation of the population itself, and we're going to divide it by the square root of n, the number of n sample sizes we had. And we're going to give it a little bit of a new name because it's actually technically a new formula. So we're going to call it the standard error of the mean. So all the averages, this is the error that we get from the averages themselves. Super cool. All right, this is the way we get to a normal distribution of any data whatsoever. It doesn't matter what data looks like. We put it like this and we are done. Now, let's do one example from the textbook. Just to sort of show it, and then from here on out, we're going to just kind of quickly do the rest here. So lots of writing down. I'll pause the video for a bit here. Okay, let's go for it. Let's do a quick example here. So if we get this, this is gonna be awesome. We're good. But this is in mathematics. Sometimes what happens is you do have to learn a skill, right? Like multiplication tables, right? There's a skill, right? You got to drill yourself with 3 times 4 is 12. 3 times 4 is 12, right? And on the homework, that's kind of what you do, right? And during lecture, some of this stuff is actually more like a aha moment, like, oh, that is so cool. We're good. And this is kind of one of those aha moments. Anybody raise your hand if you took chemistry before? Chemistry? Anybody chemistry? Chemistry? Okay, the aha moment should be in chemistry is what in the world is a mole? What is a mole? Anybody? Besides a little stuffed furry creature in the ground? That's not chemistry. It's right? The amount of units, right, of any particular substance whatsoever. It doesn't matter what it is, right? But it standardizes that, whether it's gold, whether it's helium, whether it's oxygen, whether it's nickel, right? If you convert things into a mole, then everything is the same, right? You standardize the whole entire periodic table. And now you can actually move and shift things around. You go from one to the other, having that concentration, mole concentration, or 1 mole of each one. Okay, same thing here. You guys ready? We have all but this bunch of data. So here's the example from the textbook. Here it is. The number of times 4 people go shopping in a month is given by population. The number of times 4 people go shopping once. Man, in a month. Could you imagine one shopping trip in a month? Where do they live? But here it is. I got 3 times, and then 5 times, and then 7 times. That's it. So notice the probability here is 1/4, and everybody just went, looks like just went once, right? So one person went 1 time, another person went 3 times, another person went 4 times, oh, sorry, 5 times, and one person went 7 times. So you randomly choose 2 people out of those 4 people. You're gonna replace it, and then you're gonna list all the possible size values of 2. Are we good? So let's kind of think this thinking moment here. Because once you get this, like, oh, that it makes so much sense. So does that look like a normal curve? What do you guys say? Everybody shakes their head sideways. No, that is not a normal curve. Normal curve has this nice little symmetric shape. It's big in the middle, right? And it kind of just tapers off on the sides. So the question is, can I make this into a normal curve? And this is the way we do it. We're going to take 2 people at a time, randomly selected. We good? And in fact, we're going to take all the possible 2 sample sets that we can have. And what we're going to do is we're going to figure out the average for each of those. Cool. And let's jam. And then we're going to take, let's do the sample. Yeah, we'll do the sample mean first, and then we'll do the other ones. Okay, let's go for it. So, dun, dun, dun. Here's what we do, and talk to me if this makes sense. I got a 1 and a 1. Good there. A 1 and a 3. So notice I am repeating it, right? So one person can actually be selected both times, right? So I just want to get the sample set, all the different sample sets, and all the time. So I got 1 and then I get the average. 1 plus 1 divided by 2 is 1. Average set of 1 and 2 is, and 1 and 3 is 2. Everybody agreed there? The average between 1 and 7 is 4, and we go so on and so forth. We just keep on going, keep on going, keep on going, keep on going. Out of curiosity, what number here occurs the most for the sample mean? Let's see, 5 occurs once, twice, 3 times. 4, let's check. 1, 2, 3, 4. Okay, 4 occurs 4 times, 5 occurs 3 times. Out of curiosity, 6. I'm gonna go 6. 6 occurs twice, looks like. Is that right? 1, 2. 3 occurs 1, 2, 3 times. So notice the averages are going up. So let's do this here. Let's actually plot now all the sample, all these guys right here on a frequency table. So real quick here, 5, 4, 3, 2, 1. So 4 occurs 4 times, 5 occurs 3 times, 6 occurs twice, and 7 occurs once. And we plot, so this is not plotting the data, right? We're plotting the averages of each of the samples we did. And voila, it looks like this. Is that pretty cool? I think so. Because does that look closer to a normal curve now? So here's what we do. We take data, no matter what data it is, who cares? If we can take the data, take random samples of the data, get the average of each of those, right? Average, 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 average. All the different possibilities. And we plot that data, we get ourselves a normal curve. That's cool, because didn't we deal with normal curves already? Remember 5, 3? We can get z-scores off of normal curves. We can get x placement off of normal curves. We can get probability off of normal curves, right? We have all that stuff. Okay, I think it's fantastic. So let's go back real quick here. So find the mean, variance, standard deviation of the sample means. Good. Compare your results with the mean. So if you think about this here, isn't the average here 4? If I add 1 plus 3 plus 5 plus 7, then divide by 4, that's 16, right? 16 divided by 4? I think that's 12, 12, 13, 14, 13. Yeah. Yeah, so the average is 4. So the average just stayed the same. The average is exactly the same. So we got variance here and then standard deviation. I want to see what that is here. So we got this one. Notice this guy is the same. Sweet. Okay. Now let's jump to this one here. We got this. We got this. And then we're going to compute the mean, variance, and standard deviation of the sample mean. So now we're going to do this. We're going to take a look at what is the variance here and what's the standard deviation. Do you guys remember doing those columns where what x minus x bar, we squared it? Remember we squared it before? And then we have to add them up. So we're not going to do that again. That's too long. So we're just going to compute it here. We're going to go like this. The sample mean is 4. Isn't the population mean as well 4? I think so. Variance, here it is. Variance is 2.5. 1 second, just check something out here. And then the standard deviation. We take this guy and we take the square root of that. Gives us 1.6. Okay, we're good now. Don't need to write it down yet. We'll do some examples in just a second. Okay, these satisfy the results properly of the standards because the average is exactly the same, true? So our data, as far as the average is concerned, is exactly the same. And we have ourselves, by dividing by the square root of n, we have ourselves a standard deviation of the sample that is now normalized, right? It's now actually based upon a normal curve. Okay. Just to see it real quick here with more numbers or with kind of more of a that's not a normal curve yet, right? Because I can see individual numbers here, right? So now let's kind of just pretend, theoretically, let's say we have a whole bunch of numbers. So let's say this here. Let's say we take, oh, it doesn't say what it is here. Okay, theoretically, right? Let's talk theoretically. So let's take a look at this. This is a data set. I don't know what this is. This is scores off of tests of statistics class students right here. Whoa, these guys are not doing too good. Those are the F students. They did not study, nor did they do their chapter 5 homework. So then, or they didn't do it until like 2 hours before the test. Not good. Okay, then we have the students, other students here. The B students, and then we got some A students in here as well. Okay, cool. There it is. The average for the test, let's say, was 65 or 70%, let's say. And you have a standard deviation. Are we good? Question is, can we normalize? This is just like raw data. Can we normalize this so that it becomes a normal curve? Absolutely. What we do is we take sample sizes of more than 30. 30 is the least, but if you do more than 30, and we're gonna, for each one of those, we take the average or the mean. And what happens is we keep on doing it for all the different possible possibilities, and we get ourselves this right here. We get ourselves a normal curve. The means are exactly the same, so the mean hasn't changed. But what we've done is we've balanced out the whole entire data here. Are we good? The standard deviation of the sample means, we have a formula for that. There it is. Standard deviation is going to be Standard deviation of the population divided by the square root of n. Now, what does this mean right here? Remember how we said that standard deviation should encompass about 68% of the data? Remember that? So that's exactly what this guy does. It takes the standard deviation of the population, and it wasn't like someone just came up with it one day like, oh, the square root of n, that's great, right? We kind of looked at data like, hey, where's about 70% of the data falling all the time? It falls in this little section right here. So what's the relationship between this standard deviation and the standard deviation I want? And eventually it winds up to be a very simple formula. It's just the square root of n. Okay. That should be like super cool. Okay. So now the question is this: what happens if the population itself was already normally distributed? What happens if it was like, oh, that's perfect. Like weight of men in the US, you know, some are a little bit more overweight, some are a little less. I didn't talk about the women. And so it's normally distributed this way here. So if it is, that's cool. It is still falls in line just perfectly. The mean is still the sample mean. And then the standard deviation gets adjusted a little bit here, not by much. And then it gets a normal curve. So now we have normal curves all the time. Okay, let's do an example here. Let me jump to this one right here. And let's calculate stuff. And then let's see what it looks like on a normal curve. So this one, we're going to calculate the mean, sample mean, and then we're going to figure out the standard error that we're going to get. So here it is: a study analyzed sleeping habits of college students. Okay. They found that the average sleep time for a college student is 6.8 hours. Ooh, talk to me here. Raise your hand if you sleep about 7 hours a day. About 7-ish. Okay. Raise your hand if you sleep more than 8 hours a day. Cool, cool. Raise your hand on normal basis, right? Raise your hand if you sleep less than 6 hours a day. Dang, you guys are like me. Okay. Yeah, I get about by 6, maybe just a tinge under 6-ish. Okay. So well, only one person's normal. Okay, so this one says, notice real quick here, it's interesting how it looked that this is a quick fall off on this side. But on this side, it's a bigger area over here, huh? So there's a lot more students here. Okay, so here's what we're gonna do. Standard deviation is 1.4. Random samples of 100 sleeping times are drawn from this population. And the mean of each one is calculated. So find the mean and the standard deviation of the sampling distribution. We're good? And then we're gonna sketch the graph here. So does that look like a normal curve? Nah, it's kind of heavy on the right a little bit here, right? But we're trying to figure out what does 68% of the data look like, right? We're trying to figure out what does 80% of the data look like. That's what I'm trying to figure out. Okay, so here's what we do. Let's go with it here. Can you find for me the sampling distribution mean? And it kind of tells you already, hey, the mean is the exact same as the population. So in this case, we're going to do some numbers here. So mu with little x over here with a bar. That means this is the average of the averages, technically. Average of the averages is going to be the same thing as the average, and that average will be 6.8 hours. Perfect for it. Thank you so much. Boom. The standard error, we're going to hone this in a little bit here. The standard error is equal to the population standard deviation, and we're going to divide that by the square root of n. Okay, let's do this one here. So standard deviation, write it in, X bar right over here is going to be equal to this. Here's your formula. You take the standard deviation from the population itself, divided by the square root of n. So let's see, n, that's going to be 10, right? Because it's 100 originally. So it's the square root of 100, which is really just 10, which really just becomes 0.14. You move the decimal over by 1, or if you want to try it on your calculator, go for it. Try it on your calculator. All right, I already got those numbers. Cool. Okay, let's make sure we got them. And then we're going to draw this. So if you were to draw this, 6.8 is about right here. Oh. And then what happens is we're going to go out 1.4 out one way, right? 1.4 out one more time. And so notice the data is very, very tight, huh? So let's go back real quick. Let's kind of jump between the two here. So if you want to graph this, you are going to graph about from 6.5 hours up to about like a little over 7. Cool. Let me go back real quick here just so we can kind of see what's happening here. I'm going to go back to here. Synergy, man, that's a lot different here than this one, huh? Notice the standard deviation was a lot bigger, right? 1.4, right? And it was uneven on both sides, right? It was not very even. And so keeping the average the same, notice there's a lot of people right here, right? About right there, there's a one. And then after that, it kind of goes down considerably here. And this one goes down even faster, just goes down slowly. But our problem is it's not a balanced way of seeing it here. So we're approximating probabilities, right? And we're trying to approximate the area. That's kind of what we're trying to do, the area that's underneath here. And so what we do is, there it is, distributing with n equals 100. Here's our model that's going to model the rest of the information. Okay, let's see, approaching clock. Let's kind of walk through one more example. We'll get formulas and we'll do another one. Let's walk through just one more example. Don't need to write it down. Let's kind of think with here. So training heart rates for 20-year-olds athletes, normally distributed. Here it is, 135 beats per minute is normal for them. And then you have a standard deviation of 18 beats per minute. That is the standard deviation. Let's see. Random samples of size 4 are drawn from the population. The mean and each sample distribution is calculated. Find the mean and standard deviation of the sampling distribution and sketch the graph here. So this one right here, it looks pretty normal, doesn't it? Right here. Okay, we want to standardize it. That's all. But it looks already pretty good. So 105 beats per minute. We're going to standardize the shape of it so that it gives us those 68%, the 95%, right? And then 99.7%. So we do just this right here. So average mean is going to stay the same, 135. Only change we do is we do that little formula here. We plug it in. It's going to be 18 was the standard deviation. We're going to divide by the square root of n, which gives us 9. And what we've done, again, don't write this one down if you don't want to here, because this is just me showing it. And so the normal curve, the distribution, normal distribution, now with the correct percentages or a very close use of percentages is right here. So my standard deviation lines up exactly with the percentages that I have. So one standard deviation away, that gets me about 68% of the data. 2 standard deviations away gets me about 95% of the data. 3 standard deviations away gets me about 99.7% of the data out. Okay. Now this formula you do want to write down. Crazy at first, here it is. Remember that z-score that we talked about? So here's what we're trying to do. We're trying to find a z-score of our data. So we've normalized it. We want to go from data big formula with fractions inside it. Not so fun. So if we talk about the new normal curve that we built, it's built off of this right here. So the average or the number that we want, the value, because these are averages, right? So it's the average, subtract the average of the population, divide by the standard deviation. That's how we find the z-score originally. If we push it back into the data itself, it's the x that we want, subtract the population average standard deviation divided by square root of n. Let's do a problem here together. 1, 2, tell me if you guys have written down the formulas already. We're good to go. Okay, let's go with it here. Be kind of. So here it is. The figure shows the average distances traveled by drivers each day. So for 16 to 19-year-olds, looks like they travel about 20.7 miles. 20 to 29-year-olds average about 30 miles a day. Wow. So from 30 all the way to 50 for 20 years of driving to work. That's a lot of time spent in the car. Okay, 50 to 60, 64, and then 65 to 74. We're good. Okay, what is the probability that the mean distance traveled each day is between 19.4 and 22.5 miles? So let's see. 19.4. So we're going to go over here, right? So notice, yeah, they got 20, 31, 37, 30, 30, 30.4. Okay, so let's go with it here if you want to write down just the important information here. So we want between 19.4 and 22.5, assuming we have a standard deviation of 6.5 for the data itself. And real quick here, sideways, does that look like a normal curve? Because kind of should go like this right here, right? Sideways it doesn't, right? It looks like the 69-year-olds are a little lower than the 65 to 75-year-olds. And then this kind of does bunch up a little bit here, but it's not a normal curve per se. It's not a perfect normal curve. So let's go with it here. So by the CLT, the central limit theorem, because we have more than 30 people here, we can figure out a normal distribution curve that approximates this. First things first, the average is going to be the same, right? 20.7. That's good. And so what we're going to do is, since there's a lot of people in here, we're going to take sample means of 50 at a time. That's what we're making. We're making sample means 50 at a time. We're going to take the standard deviation of the population itself, divided by square root of 50, and give me that answer, please. .9 is perfect, okay? Got 0.9. So now I have a normal distributed graph. True. Went from a non-normal now to a normal. That's cool. Standard deviation, I calculated it so that my percentages are now nice. It is a normal distribution curve. Okay, so real quick here then. If we're at 20.7, what I need is something we've been working on before. I need the z-score. I need the z-score for 19.4. Then I need a z-score for 22.5. You guys remember finding the z-score, how we do that? Again, kind of jumping into the weeds of math here, right? So here it is. Let me do the first one. You guys get the second one, like we did last time here. Z-scores corresponds to sample means of 19.4, 22.5 are found like this, right? You take Z1, remember, because we have a lower bound and an upper bound, right? We take the score that we want, subtract the average. And because these are sample means, what we've got to do is we've got to do 6.5 divided by square root of 50. Or you could just use one from the previous. Did we know this one right here? 0.9. Except the only thing is you want to do, if you're going to do that, might as well keep like 3 or 4 or 5 decimal places just for accuracy's sake. Okay, on your calculator, try this one. Raise your hand if you don't get a negative 1.41. I'll come by. All right, if you did get that one, try the second one. Try the Z2 by yourself. I'm going to pause. Okay, class, let's talk about our calculators then real quickly. Let me do it the wrong way first, okay? Then we'll go from there. So if you go 19.4 minus 20.7, you click enter. That's probably the better way to do it just because you have that whole piece by itself. We good? It's all done. Now the question is, how do you do the rest? Well, notice that the 6.5 divided by the square root of 50 is all in the denominator, right? It's all that one big piece in the denominator. So when you divide, when you click divide, that gives you that answer. Negative 1.3 goes up here. Divide by, and what you have to do is you have to put in parentheses here because you're trying to keep the 6.5 divided by square root of 50 all inside the denominator. If you don't, this is what's going to happen. You go 65 divide by square root of 50, and you got yourself the wrong answer. We're good? How many got negative 0.002828? Even if you got it, you probably wouldn't say it, right? Like, why would I tell you that I got it wrong? Okay, let's do it the correct way. So 19.4, and I'll do it in like one shot as well. So here's 2 shots. There. We're gonna click divide by, and now we're gonna keep all of this inside the denominator. So we're gonna put parentheses, extra parentheses, 6.5 divided by the square root of 50. So now notice those extra I'm going to close off the parenthesis for my square root. Now I'm going to close off the parenthesis for the whole entire denominator. I have kept that in my denominator now. Enter. Voila. We good? Okay, so the question comes up, Mr. Hunjiev, How could I do it all in one single step? There's a way to do it. Yes. All we got to do is just put extra parentheses for the numerator as well. So let's start off like this. That 19.4 minus 20.7. Let's keep that all together as one big piece, which is what parentheses do. So numerator, all one giant big piece with parentheses. We good? Cool. Divided by extra parentheses, all one big giant piece for our denominator, which is 6.5, divided by square root of 50. And here we close off the square root symbol, we close off the denominator, all of it. We good? Now we've done it all one single step. Clicked enter. Hey, I love correct answers. Okay, your job. Can you guys do Z2 based upon 22.5 miles? I'm gonna pause this and I'll see how many people got correct without knowing the answer. All right, class, let's go with it. I think everybody got this one here and we got ourselves. Let me do it real quickly here. 225 minus 20.7, even though everybody got it here. I like to do it in 2 steps because that allows me to have that. Close off the parenthesis, 6.5 divided by. Now you guys with TI-84 calculators, you guys are so cool because when you press the square root button, you guys don't have a parenthesis. This kind of slides down and the square root button kind of becomes bigger across. So you won't need the extra parenthesis that I'm going to do right now. We don't need that one. You just move your arrow key to the left and you click on closing off. So you should have just one parenthesis, one that opens up before the 6 and one that closes off the whole entire problem. And you get yourself 1.598141856. That's what you got. Okay, we're going to round off. Z-scores are always rounded off to the nearest hundredth. So give me the Z-score to the nearest hundredth. And you guys all had it on your sheet of paper. So yes, 1.96. Now, almost there, guys. Now can you give me the probability that the mean distance driven each day, a sample of 50 people between 9.4 and 22.5 miles. So here's what I want to see. I want to see, I'm going to give you the answer. I won't give you the answer yet. Do you guys remember on your calculators? All right, we can do it. Let's see. Yeah, on the calculators. I think we did that before. Can you calculate the Z-score based upon that one, that one? And the Z-score is now, let's see, we did this, something about normal curve, something distribution. Click the distribution button on your calculator. You got a Z1 score and you got a Z2 score. And your mu, your average now is just 0. And your standard deviation is 1 because we standardized everything just now, right? So let me show it to you then. So clear this off. We're going to go to distribution right here. We're going to go to down to this one right here, number 2. Click enter. And we have ourselves a negative, oh, no, negative 1.41. The beginning Z-score, the ending Z-score. And because we have Z-scores, we've normalized it back to the average being 0. We good? And the standard deviation being 1. That's it. And let's see how many 16 to 9-year-olds drive between 19.4 miles per commuting to 22.5 and click enter. And roughly 90%-ish, right? 89.6 if you want to be precise. And that's what we have there. So about 90% will drive an average distance between those two numbers. Okay. So the way you do that on a table though, remember, because the table always does it from the left on, right? So if we did it by table, we look the high value up. Let's do we have some time? See what else do we got to get to today. Now, if you did it by table, I'm not gonna make you guys do it by table. You would have got for 1.96, you would have got 97.5. Okay, let's do it by table, just real quick here. So back of the book, go all the way to the back of the book. You look for the positive z values and you look for what's the value for 1.96. And so just real quick, so we know again, right? So what we do here, because the z values, right? The z values, let me go back up real quickly here. It's trying to say this right here. You're trying to say at 1.96 z-score, I'm getting all of this right here. I'm getting everything going off to the left. And what I have to do is I have to subtract out anything that's the left of negative 1.41. When I subtract that out, like this right here, I'm going to subtract all this out. And when I subtract all that out, I get myself all the stuff that I want in the middle. Then I get myself all this stuff right here. Oh yeah, this should be negative 1.4. Okay, guys, please try it yourself. Take a look with your neighbor. Do it together if you need to. So as you look at a table and you look for 1.96 as a z-score, you should get a area of 0.9750. Everybody got that one. And then let me explain real quick. And then you look for a z-score of negative 1.41. You get this one, and you subtract them from each other. Okay, good, and getting ready for break almost. Let's try one. This one, if you notice, this one is in the middle, right? You kind of trap between two z-scores, right? Let's do one where you actually are not trapped between two z-scores. So one more example, and we'll take a break. The average room and board expense per year at a 4-year college is $10,453. Out of curiosity here, is that West Coast College? Anybody lives in the dorms? How much is it for the dorms for the year? Forgot. Okay, yeah, it's kind of like one of those. Okay, yeah, in-state versus out-of-state is also an issue there too. How much is that going to be? Okay, you randomly select 9 4-year schools. What's the probability that the mean average or the average room and board is less than 10,750? So again, you assume that the room and board expenses are normally distributed. You got a standard deviation of 1,650. Oh, hold on. The important word here is this right here. Assume that the room and board are normally distributed, right? If they're normally distributed, I can use my z-score, or I can go directly from the data, can I? Because once I make a normally distributed curve, I can plug in stuff directly into calculator. We good? I don't have to use 0 and 1. I just use what's provided. So let's jam. So on your calculator, let's see if I get a, whoa, that was crazy. Oh, my front cover here. Hit the textbook here. Okay, we're going to punch this into our calculator. So I want to just show you the graph first, though. So again, the important word here is normally distributed. Once you see that word, we can use our calculators because it's been normalized already. We're good? Or it's very similar to a normal curve. Okay, so let's see. Because the population is already normally distributed, we conclude that the distribution of sample means is normally distributed as well. Therefore, the average is this. And this is going to be our standard deviation. Are we good? So we still use this one, but let's calculate this already. So 16, 50, 12, yep. And good, let's go with it here. So can we find the z-score that corresponds to the value itself? So 10,750 minus 10,453 divide by this right here, or you can just calculate it previously already here, right? Or you can just say, hey, it's 550. It's a lot easier to sort of think about if you calculate it. So 0.54 is the z-score. If you did it by table, you're looking for a z-score on the table. So can you guys find on your tables, can you guys find a z-score of 0.54 and see if you guys get this same number right here? So about 71% of those guys have. Okay, did you do it by table? That's cool. Let's do it by calculator real quick here. And then what you can do is you're going to punch in this right here. You're going to say normal curve. You guys tell me, how come we use negative 10,000? Negative 10,000. Because we want to cover all the area, right? That's underneath the curve all the way down, way, way, way past. So remember, the calculator can handle z values if they like, or the calculator actually can handle x values directly, right? So let's do x values directly. So negative 10,000 all the way up to 10,750, which will be the end, the average is 10,453. And we're going to punch in 550 because that was for the sample means, right? That was to normalize the curve. Okay, we good there. Just talk to me. Anybody did not get that? Raise your hand, I'll come by. But just try it on your calculator or your cell phone. Try this right here. Raise your hand if you don't have it, I'll come by. Otherwise, I assume you have it. We'll keep on going. So about 71% of such samples with 9 being the end score will have a mean less than 10,750. Okay, one more problem. Let's see if we do one more. We're good? Cool. All right. So one more problem, which actually has 3 subproblems here. So some college students use credit cards to pay for school-related expenses. Wow, that's crazy. For this population, the amount paid is normally distributed, and the average, wow, this is actually from Sally Mae. So this is actually correct data. So average is $1,615 to pay for school, and a standard deviation of 550. So I got 2 things here. What's the probability that a randomly selected college student who uses a credit card to pay for school-related expenses paid less than $1,400. Here it is again. It's normally distributed, is that right? So number one, let's see, what's the probability of randomly selecting college student who uses credit cards is 1,400. So in this case, let's find the z-score. So this is the way we did it in 2.3. We got a z-score of negative 0.339. Okay, good. And you guys, let me just check. And you guys talk to what's the probability that has happened? Punch in the z-score. Let's see, we're going to go paid $1,400 or less. So very similar to the last problem that we did, right? Something about having a negative 10,000 in there. So let's see distribution. I have a z-score on my hand, so I gets normalized. So negative 10,000 up to a negative 0.39. Since it's normalized and I'm looking with the z-score, that means I'm going to go 0 is the average, 1 is the standard deviation, and voila. Okay, probability should be about 34%. We got 34, 35%, which we got by calculator. So this one, way we're doing it this way here, this is a 5.3. We good? 5.3. We're not doing sample means here. So let's go back to our original problem. For number 2, you randomly select 25 college students who use credit cards to pay for school-related activity. What is the probability that their mean amount is going to be less than 1,400? So now you're talking about randomly selecting the probability. And you're looking at now the averages, right? Now you're looking at their mean, right? What's the probability that their average will be paid less than? So now this is 5.4. We're going to think about the error that's happening because we're thinking about the mean. So let's jam with it. So the z-score that follows just a little bit different now. It's the one that we were just practicing today. So it's the 1,400 minus the 1,615, but then we're going to divide it by 550. Also divided by the square root of 25 because that is the number of samples that we have. All right, and try that one. Let's see if you guys get negative 1.95. Cool. So punch this in on the calculator here, and you should get something that looks like this. Let's do it together here. I think we did last one together, right? Okay, let's go with distribution number 2. So we're going to go negative 10,000 again, up to a negative 1.95, 0 and 1. Phew, okay. 0.0256, are we good? That's the same thing. So this is actually what? This is actually 10%. This is actually 3%, right? 2.5% really. So if we were to make sense of this here, I see you guys are dying already here. So we'll take a break after this, definitely. Here's what we got. So although there's a 35% chance that a college student who uses credit cards to pay for school related expenses will pay less than $1,400, there's only 3% chance that the average amount of sample of 25 college students will pay less than $1,400. We good? So one is just the data itself, and one is to saying, hey, if I'm going to do a survey, right, of 25 students, here's my expected value that I'm going to get. Okay, so because that there is only a 3% chance, right, the average amount of sample of 25 college students that will pay less than $1,500 is very, very unusual at that point. Okay. Okay, one more thing we got to do here is something called normal approximations, or approximating stuff, something called to binomial distributions. What in the world are binomial distributions? Binomial just means like success or failure, one or the other, which means it is, first of all, it's discrete, right? And you can only have a yes or a no on the data itself. And we're going to try to figure out how to work with it here. Let's see, success, failure. It's more like, remember how we had, the ACL surgeries. You guys remember those from like chapter 3? It was the success of an ACL surgery is like 95%. So you have this, so like success, then you got a failure, which is 5%. So how to deal with those kind of combinations of things. So again, one slide with a lot of writing. Lots of writing here. So here's what we're trying to do. We're trying to get things that have success, failure, yes or no. We're trying to get that into a normal distribution as well. All right, so can we even do it? That's what this says right here. So we can only if a few things happen. If the number of sample spaces times P is the percent of successful trials, or what we want, it's going to be greater than 5, and number of N values times the Q is the opposite, number of failures. If those guys are both above 5, then yes, we can approximate this with the normal distribution. So now the question is this: what's going to be the average? What's going to be the mean? And how do we calculate standard deviation? So the mean now is not the same what it was before. Like the mean is going to be number of n values times p, or the number of successes, or the number of yeses. Standard deviation becomes the square root of n times p times q. So n means the number of independent trials, p is your success rate, q is your failure rate for that single trial. All right, sometimes it's just a matter of upping the number of trials that you're using, and that can get you what you need as well. Let's see. So it's 5.4. What we did is we made any kind of data, as long as it's continuous data, right? Like miles, if you drove certain miles in a day, that would consider that continuous data. Number of hours sleeping, that's also considered continuous data. So 5.4 really dealt with continuous data. That we could do. Switching to 5.5 now. The question is, what happens if you perform surgery at 95% success rate? You're going to do 3 trials. Can you approximate that by a normal distribution? That's the question. Cool, then good. So let's do this here. Depending on what the data says, what we could do is we could just increase the number of trials. That's all, and that kind of gets us into wherever we need to go. So maybe just a quick graphic here. Let's do this here. This is a graphic normal distribution. I'm not sure what this means. Maybe like the number of children in a household. That could be it right there. We're good. So we have about 40% have 1 child, right? About 32% has 0 children. So you can only have specific ones. It's discrete data at this point here, right? So what you do here is n is equal to 4. Notice the data looks like this right here, right? I'm sorry, real quick here. Sorry, that was discrete data. Normal data is success in a certain trial, right? And let's say the success was 25%. Your failure rate is 75%. And then your n value, you did 4 independent trials of it. So notice what happens is the data is not normal yet. You do 10 trials and it's kind of getting a little normal. 25, by the time you're at 50, notice this is a nice normal curve at that point. So yes, we got something that was a 25% success rate. Each and every single trial, we've made it into a normal curve. So we can now approximate it. And again, the whole game is I could use the z-score. That's what I want to be able to do. Can I use the z-score? All right, so let's jam. Let's try it here. So first things first is we're going to try to see if we can or cannot use the z-score first. Let's just try that experiment. And then we'll try to figure out how do you make it a continuous function. And then we'll do one example, but I think we're going to have time run out between that. Okay, survey of 8 to 18-year-old heavy media users, and you ask 47% say they got fair or poor grades. So the question is there a correlation? Is there a connection between heavy media usage and poor grades, I guess? You randomly select 45 18 to 18-year-olds heavy users in the United States and ask them whether they get fair or poor grades. So question, can we use a normal distribution first? So let's go with it here. I'm going to jump to this slide here. So tell me real quick here, does that make sense? We're at 45 because n is equal to 45. There was 45 people in the survey. The p-value said that 47% of those are great. So then we would do the opposite. We go 1 minus 47 or 0.47 gives you 0.43. We're good there. So it's just a little test right here. The question is n times p. You multiply those guys together. Is this guy greater than 5? Yes or no? Go for it on your calculators. Let's see what we get. I go that, boom. Okay, next. The other way. And we're good both ways, right? So because n times p and n times q is greater than 5, we can use the normal distribution. So now let's go for it here. What's the average? And then give me standard deviation at that point. It's all over here. Okay. N times p. Anybody got n times p? Oh, we already have it, don't we? 21.15. We go back up here. So I got an average. My average for this is 21.15. So it's from 45 users, 47 of them saying yes to poor grades. Okay, then we got the other. Standard deviation is the square root of n, then times p, then times q. Tell me when you got it. And then tell me what it is. .3.3-ish or 3.35, 3.4, somewhere right in that range. Probably 2 decimal places would be okay with that. 3.35 is cool. So we can use the normal distribution. There's my average. There's my standard deviation. That's all I need. And if we were to now do some questions off of that, we can use those numbers. We're good. So if you randomly select, or how much of them would say that, see. Okay, if we were to take a look at a graph, if I was to go and start graphing this, you don't need to graph it, but it looks like this. Does that look like a normal curve right there, getting close to a normal curve? Absolutely. Okay, so that's one. Let's jam with number 2. How about this one? Can you guys do the same exact thing for this one? In the survey, same thing here. 8 to 18-year-olds. Now light media users in the United States. 23 of them say they get poor or fair grades. You randomly select 24 of those users and ask them whether they get poor or fair grades. Question, can I use the normal distribution here? All right, so I guess we need to multiply n times p, see what we get, right? And then n times q, see what we get there. So let's go for it here. So n is equal to 20, we've got 20 users, p is 0.23, q is 0.77. Let's go with it here. What'd you guys get for NP? I got 4.6, And Q, at that point, we don't even care for about NQ. Like, nope, with 20 people in the survey and your success rate is 23%, it's not going to lend itself to normal distribution. So it's not going to work well. And so notice if we were to graph all the averages, right, and put them in a grid, we would find out that like that does not look like a normal curve. Okay, good. So question is, can you use it? Can you not use it? That's the first question. Second question is, these are discrete things. Notice, like you can't have, like you're going to have surgery, right? You're going to have 3 surgeries, right? You're not going to have 3.5 surgeries. That does not make sense, right? But what we're trying to do is we're trying to get it back to a normal curve. So we do this thing. It's called the correction for continuity, because these are trials, right? 1 trial, 2 trial, 3 trials. In order to make them into a continuous sort of process, and they're all numbers, right? They're kind of like 1, 2, 3, 4, 5, right? So all we do, which just kind of makes sense, we're just going to expand it out by half a unit this way, half a unit this way. And so now these guys are actually touching. And now I have an area underneath here. We good? I did not have an area before. Now I got an area. So by extending out to 0.5 units to the left, to the right, I've now just made a continuous curve now, at least approximately continuous curve. Okay, so let's try this. Say again. Oh yeah, sure. So let's say we're doing trials of surgeries, right? ACL repair, right? So you have surgery 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So notice the surgeries are just numbers, right? But for miles per hour, you can do 12.67 miles per hour. That's a continuous kind of thing, right? So we're trying to figure out, how do you get number of surgeries, which is 4, right? Or 5 or 6. How do you get it so that it's now continuous? So it looks just like miles per hour. And so what we do is we stretch out, instead of just having that 4, we're going to stretch it out to anything between 3.5 to 4.5. And now what you've done is you've kind of stretched out, again, this is a normal curve, right? You stretched out the normal curve now, and now you have something similar to miles per hour. So let's do an example. I think an example would help here as we do it. So if you were to look for a probability, right? We're trying to do probabilities now. Probability of a value, any kind of value, between 270 and 310, inclusive, right? So all we do is we think about probability, but think about these guys are 270 surgeries, right? 271 surgeries, right? Can't do babies in a family. That's too big. So surgeries is fine. 270, 271, all the 310. In order to make this a continuous curve, what we're going to do is we're going to just go down by 1 or half, and we're going to go up by a half. And now notice these are now X values according to a normal curve. Now, if I can, I can convert these to Z values at this point. We're good? As long as I know what the average was. If I knew what the average was and the standard deviation, I can convert this to Z scores at this point. And it kind of includes everything here. All right, that's between 2 things, right? Remember, that's when like we have shades on Z1 and Z2, right? That's kind of what we're looking for. Okay, how about now? How about this probability of getting at least 158 successes in a trial? Let's see, is that a bottom Z-score or is it a top Z-score? Is it bottom and you're looking for the area going up, or is it a top Z-score and looking for areas going down? What do you guys say? If this was a trial like this, I don't know where 158 is. I'm not sure if it's in the middle. I'm not sure if it's like exactly in the middle, if it's on this side or this side or this side. I don't know, but at least 158. Cool. It's going to be a bottom z-score. We'll call z1, and then we're going to try to figure out that area there. We good? I just don't know what 158 is because I don't know what the average is yet, because that's what we're trying to get to. So I'm not going to use 158 because those are successes of surgery. Which value should I use for my average? So I have 158 surgeries. I got 159 surgeries. I got 160 surgeries for a particular doctor, let's just say. So to find the z-score, I'm going to use 157.5 because that includes the 158 inside it. We good there? If I just use 158, I exclude some of that area that actually includes the 158. So we want to be able to include as much as we can of the number. We good? Okay. One more. Probability of getting fewer than 63% successes. So again, normal curve. I don't know where 63 is. I have no clue. Could be right in the middle, could be a little bit less than the middle, but I'm looking for fewer than 63. Going this way. The question is fewer than 63. Should I use 63.5? Should I use a 62.5? Right? Because I'm going to go out one way or another. And so what we do for this one, what we're going to do is we're going to use a 62.5. So if we want to go to the left, we go up to, we want to include the 62. We don't want to include the 63. So we're going to cut it off at 62.5. We're good. All right, on page, let's see what page, if you want to write this down here, on page 277, this is probably one of 277, it has that little piece right there. If you're trying to find exact values, at most, then we take the C value, we add fewer than, we subtract, at least, we go greater than, but subtract, more than. What we do is we go C value, add a half, and then you're going to do a greater than symbol. So 5 different ways to write it, depending what you say in English. We're good? So kind of keep that. That's a good page to sort of see those on. You know, I think we can finish here. If we can just go, we got 1, 2, we got like 6 slides to go. I think we can probably do that. Let's go with the numbers we had before here. So we're not doing new numbers here. So let's go with this one right here. Let's go back to this one right here. So I got a survey of heavy media users. United States, 47 said that they got fair or poor grades. Is that right? You randomly select 45 of them. Ask whether they get 4 grades. So the question is, what is the probability that fewer than 20 of them respond yes? Fewer than 20 respond yes. Let's go for it here. If you want to write these numbers down. Remember, our average was 21.15. Standard deviation we calculated was 3.35. That's cool. We can use that. So now let's see. Fewer than 20 of them respond yes. Okay, so fewer than 20. Let's go back to our little list here. Do we want to include the 20? Right? Fewer means I'm going to go down a little bit here. So 19.5 is what I want to use for this one here. So fewer than 20 says I'm going to trigger out the probability of X being 19.5, even though, again, can't have 19.5 people, but we just made it a continuous, or at least approximated by continuous study. So let's jam. Let's go with it kind of quickly here. Let's see if we make sense here. 19.5 is what we need. Let's go with it. So normal curve, yes, we know we can do a normal curve on this. Standard deviation is 3.35. We're looking for the shaded area, right? Because the average is 21.15. We're looking for anything that's below or on 19.5. So let's find a z-score. Z-score is 19.5 minus 21.15 divided by 3.13. Give me that answer. Negative 0.41. 49. Yeah, cool. Awesome. Okay, so if you were to go to a normal table, you can find this one on a normal table, or just use your calculator. Can you guys use your calculator to find that value there? So again, so check out your calculator real quick here. I'm gonna try to finish here because we got just a little bit here. We got, let's see, we got two more problems that should be real quick here. Okay, I'm gonna jam with it here as well. So how about, hey, I don't have my calculator now. All right, distribution, z-score. I got myself a, let's see, I'm going to go down to the left. So a negative 10,000 up to a negative 0.49, going from 0 to 1. Or 0 is the mu, 1 is the standard deviation. And are we good? So about 31%-ish. Good. Okay, we got the next example. I think we have one of two, there's last two here. So a study on aggressive driving found that 47% of drivers say they have yelled at another driver. Sure, you guys, raise your hand. Have you guys yelled at another driver? Road rage here. You randomly select 200 drivers in the United States and ask them whether they have yelled at another driver. So the question is, what's the probability that at least 100 drivers will say yes? Let's go for it here. So again, we're just practicing with z-scores. We're practicing putting into continuity or continuous functions here. So let's go with it. First things first, we've got to calculate our NP and our NQs. So 200 drivers at 47% gives you 94. 200 drivers at the complement of 47% gives you 200 times 0.53, 106. Yes, this can be approximated by the normal curve. They're both above 5. And then our average is going to be n times p, which is 94, which we already have right here. That's the same thing. And then the standard deviation. Remember that formula? Square root of n times p times q. You guys do it on your calculator as well, and we get our answer of 7.06. That's perfect. Okay, so now the question is this. At least, this is going to be at least. Does at least include the 100 or does not include the 100? Flip back to page 277. At least means we include the C value. So if this point, we're going to do this here. We're going to look at 99.5. So we're going to include the 100 in there. We're going to go down just a little bit here. But then what we're looking for this right here. Let me kind of give the next slide. We're looking for anything above 99.5. So here it is. Average is 94. Perfect. Standard deviation 706. And then we're looking for a shaded region to the right of 99.5. All yours, try that on the calculator, go, or on the table. You have to convert to z-score, right? So the z-score is going to be 99.5 minus 94. You can write it like that if you like. Let me just go back up just a little bit here. So it's this piece right here. So we already have the 7.06. And so it would have been just dividing that by 7.06. That's fine. 0.78 is our z-score. Perfect. Okay, so now let's go finding it on a calculator or on the table in the back of your book. So looking for that. I already have the answer on the bottom, looks like. Z-score of anything greater than 0.78. Now remember, on your textbook, they're always going to the left, correct? They're always going to the left of the textbook. And so what you have to do is you have to take the complement of that right there, and you should get 21. Let's do this on the calculator. So again, distribution, moral curve, boom. We're going off to the right this time. So that means 0.78 is the low bar over here. And we're going off to 10,000, 100,000, a million, who cares? As long as we go to the right shade of our normal distribution. Okay, since it's the z-score, we have it standardized. So the mu is 0, the standard deviation is 1. Click on it, and we got ourselves about 22%, 21.8 of the drivers from the survey would say, yeah, I yelled at them. Absolutely, I yelled at them. They were going so way too slow, serious. Okay, one more to finish it off. Here it is. The National Football League retirees. They have to be ages 50 or older. Found that 62.4 of them have arthritis. Oh, this is interesting. So this comes off of that movie with Will Smith. Remember that, about concussions and how the NFL tried to downplay concussions? Now the question is this, and maybe this will kind of bubble up to the surface. Does playing football lead to arthritis? Is that a normal thing? Is that something that's different here? So you randomly select 75 NFL retirees who are at least 50 years of age and ask them if they have arthritis. What is the probability that exactly 48 will say, oh, wow, hold on. This is the first time we're doing exactly. Exactly 48 of them are going to say, yes, I have arthritis. Okay, this one. Remember, we did the left side, we did the right side. Now we're going to do like kind of like the middle here. So let's go with it. So first things first, we've got to check n times p. Multiply that, make sure you get the same thing I did. I got 46.8. N times q. Multiply that, you got a 28.2. Yes, we can approximate it by normal distribution. What is the average? What is the average here? 46.8, exactly the same thing that we had over here. And then what's the standard deviation? 75 times the p times the q, and eventually get a 4.19. Again, pause the video if you're doing this at home. Pause the video, try it yourself. Make sure you guys did it yourself. Okay, but here, our goal is to try to figure out the exactly 48 of them will say yes. So because it's discrete mathematics, right? We're going to bump it out a half to the left, a half to the right. So now we're looking for anything between 47.5 and 48.5. Average is 46.8. Standard deviation is 4.19. And let's go with it. Let's figure out the corresponding z-scores for each one of those. So again, we already have that on the bottom. We don't need to do that again. But the lower z-score is going to be a 0.17. Again, try it yourself in the calculator, see if you get it. The upper z-score, z2, is going to be a 0.41. Perfect. And if you did it by tables, remember, if you do it by table in the back of the book, you have to subtract the big one from the small one. So in this case, it's going to be probability of the Here's what we do. So this is the X score, probability of the X score. We've changed it to probability of the Z score. And we're looking for area underneath the curve this time. And because everything goes off to the left on the table, this is going to go to the highest one, subtract the lower one. And at that point, we get ourselves this and this. About 9%. 9% are going to say yes. Let's try it on the calculator. Calculator's so much better because it calculates the z-score between them here. So second function, distribution number 2. And we're going to go from a 0.17 or 0.17. We're going to go up to a 0.41. And we've normalized it. So it's going to be from, let's see, the mean is 0. The standard deviation is 1 since it's normalized. And the answer is exactly what we got here. So we have about 9% of the athletes are going to do that. And again, that's an interesting thing that comes up is what health effects do you get after certain games, basketball? You know, do you have knees that don't work, ankles that don't work anymore, you know? And then the question then becomes, should they be compensated? That's the next question. So all this stuff, good real life example. And we're going to stop. This is the end of 5.5 and we have finished off chapter 5.